So after this, before 10, everybody should wait in the waiting room. I will only click once to admit everybody because it will be a hassle to me to every time click admit. Unless I find another way to automatic enter the room. Anybody knows how to do in Zoom for the student can automatic enter the room without me clicking the admit button? Kalau tahu bagi tahu lah. Saya tak tahu, so I have to every time click. So siapa yang datang lambat tu menyusahkan saya. Okay, right. Have you put all your names, symmetric number there? Okay. Right. So who remembers where did we stop last time?
Intrinsic.
Mana?
Intrinsic semiconductor, madam.
You say it louder and clearer. Tak dengar.
Intrinsic and extrinsic.
Intrinsic and extrinsic. Okay, is that right, everybody?
Yes, madam.
Yes. Just pause the extrinsic.
But we stop at carrier concentration, no?
Yes, correct.
Okay, intrinsic,
Carry density. Yeah.
right? So the way I put some mark in my slides are the carrier concentration. So okay, those who are not turning on your video, you have 1 more minute to tell me why. If not, I will remove you from the class. Okay. And then for those who come late, after this class, I will not admit anymore anybody who comes later than 10 o'clock. 10 o'clock, everybody should be already in the waiting room. I just click one click, everybody turn in. If you don't want to attend, you don't have to attend. But if you want to attend, make sure you're on time. And if you cannot be on time, you have to explain why. Itu nama adab lah, belajar. Okay, and I don't have to tell you every time you have to turn on the video. I will just kick you out. Okay, next time. Ni kali kedua dah saya warning benda sama. Tapi ada lagi orang buat. So next time I will just okay. Unless you tell me why. Okay, Afika dah beritahu Abdul Rahman is not telling me. Ada lagi yang masuk. So if you don't turn on your video and you don't tell me why, I will remove you. So Farhana, why you came late?
Sorry, I just woke up.
Okay, as I mentioned to everybody, if the students not there at 10 o'clock, I will not allow to admit next time. So this time boleh lagi, lepas ni saya tak add dah. If you late even 1 minute late, that's it. You won't be able to attend. So you have to prepare yourself. 9:59, 9:58 already in the waiting room. Unless you have other reasons that you have to tell me, your mother sakit ke apa kan. Okay, so carrier concentration. So let me share my screen. Okay, can you see my screen? Boleh kan?
Yes, madam.
Alright, so last time we stopped at carrier concentration. What is carrier concentration? Somebody?
Number of free
Number of
carrier per unit volume.
Number of carriers per unit volume. Okay, correct. So carrier concentration is very important because it tells you how good the material as a conductor or as insulator, right? And as I mentioned before, sorry. Yes. As mentioned before, different semiconductor have different band gap. So silicon have 1.1 EV. As I mentioned, the band gap is like the thumbprint, right, of the material. So germanium is zero point 0.7 EV. Germanium is a semiconductor. It has a lower, smaller band gap. Gallium arsenide is slightly bigger, 1.4 EV, and zinc selenide is 2.7 EV. Okay, and each of the semiconductor not only having its own different, what you call it, different band gap energy, but you also have different mass. Dipanggil effective mass. Okay, so the effective mass of the electrons ni ME ni effective electron mass. Yeah, you can see here the ME has a star, right? This star means effective. Okay, and MH here is the mass for whole, and the star means effective. Effective means it's unique to the it's like relative to the material. So that's why the number you multiply by the M0. So you can see for gallium arsenide, silicon, germanium, and zinc selenide, the mass is different. The effective mass of the electron holes are different. So the lighter the mass, meaning the smaller the number of the mass, it means that the carrier can move faster. So if you want a device which has fast to turn on, turn off, like for switching, turn on, turn off, for your digital, for your processor, you want something with a low mass. So you can see here, if you can see here, saya padam ni, right? So you can see gallium arsenide has a very low 0.067 electron mass. So normally, silicon is the one that normally people use. Why? Can anybody tell me why? Why all integrated chip, most of the integrated chip are using silicon as the material? You don't know? Anybody took VLSI design? I remember some of you already have taken VLSI design, right? So I'm sure you know why all integrated chip are using silicon. Siapa yang ambil VLSI design? Sila mengaku. Kalau tak mengaku, saya doakan awak akan fail semiconductor device sebab menipu dah kelas saya. Tak berani.
Saya madam, saya.
Mohaimin seorang je ke?
Saya madam.
Saya, madam, saya. Saya, madam.
Bagi nombor ni. Okay, tiga orang je.
Saya sekali.
Tiga orang je.
Saya.
Siapa so Mohaimin, Siti Nabihah dengan Munirah, ada lagi ke?
Saya. Dengar tak madam?
Okay.
Jahat.
Okay, thank you for answering. So, next time
Jahat madam.
sampai saya doa, so jawab terus. Okay. So why do you use silicon for integrated chip? ambil dengan Prof Anis kan? The
Ah.
best. So mesti awak belajar banyak. Okay, so tell me. Why silicon? Siti Nabihah.
Sebab silicon dia lagi stable and then
Dia lagi
kalau tak
stable.
silap saya and then kalau tak silap saya dia ada smaller leakage current. Itulah yang saya tahu.
Oh, okay. Stable tu macam mana?
Macam mana?
Material lain tak stable tu?
Most stable silicon lah. Yang lain okay je. Tapi silicon most stable.
Oh ya. Yeah. Awak ambil daripada reference mana? Buku mana? Tok Guru mana cakap macam tu? Nak saya tanya Prof Anis. Just kidding. So, Muhaimin, why silicon?
Abundant. Kita boleh dapat ada everywhere. Can sand is everywhere, so we can low cost and senang nak cari lah.
Okay, brothers and sisters, answer dia bukan sebab stable lah. And stable kebanyakan semiconductor device, material lain semua stable. Okay, answernya because it's the cheapest. We engineers, if you want to buy a thumb drive, right? You want to buy a computer, you want to buy 5,000 ringgit ke 2,000 ringgit? Tu lah, of course, right? So all of us like cheaper things. So if electronics going to be cheap, if the electronic devices or the equipment need to be cheap, maknanya integrated chip tu it needs to be cheap. So it has to use cheaper material. So silicon is very cheap. Why? Dari mana silicon dapat daripada mana?
Sand.
Sand, yes. So you can go to the pantai, to the beach, go get the sand. What is sand? Sand apa dia punya composition? Macam mana ni?
Silica
Silicon
oxide.
Silicon dioxide, yes. So sand sebenarnya silicon dioxide. So if you burn the oxygen, you remove the SiO2. If you remove the O2, then you left with pure silicon. So then it become very cheap because you can just take from the sand. Okay, Hazim, why were you late? Kenapa lambat? Hazim Salam, are you there?
Yes, sir. Yes, madam.
Yes. Why did you come late?
Because I have a stable connection just now.
Okay. So you also cannot turn on the video lah because of that. Okay. Right. So where was I? So silicon because it's cheap. Okay, brothers and sisters, and it has reasonable electronic properties. So let me share again. So that's why kita semua pakai silicon. Kenapa tak pakai gallium arsenide? Sedangkan so silicon group berapa?
4.
Group 4, yes. So silicon is in group 4. Trying to get in, okay. Okay, silicon is in group 4. But if you look here, silicon, here, apa ni? The mass of the electron in silicon, the mass of the silicon, the mass of electron in silicon compared to gallium arsenide, jauh beza. You can see how many more times that the gallium arsenide is much lighter, which is mean faster compared to silicon. But in the end, all of the of the integrated chip are using silicon. The main reason because it's cheap. It's easy to find, therefore it's cheap. Gallium arsenide is from a group 3-5. And it's more difficult to find. It's more expensive. However, high-end electronics are using gallium arsenide. For example, if you want to use it for military tak boleh lah slow everything need to be very fast. For military, for satellite at space, they will use different material because they want to have a better performance. But normal like you and me, we just use it for our daily life, then silicon is good enough. Okay? So, and I will tell you another reason why gallium arsenide can be better next time when we talk about direct and indirect bandgap material. Okay, you can stop me anytime if you don't understand. So, right, so this is a graph. Can you see this graph? This is a graph of intrinsic carrier density versus temperature. Okay, bawah ni is 1 over T. So don't get it confused. And I like to give this graph as well inside in the exam or quiz. And the student always confused. I think the student doesn't know how to read graph. Okay, so we engineers, we need to know how to read graph. This is here at the bottom is 1 over T. It's not T, it's 1 over T. And at the top here is T. So you can see the numbers here, the getting from big to small. This is small to big. Okay. So if you look here, the intrinsic carrier concentration, we talk about intrinsic material, and also we talk about the extrinsic materials, Bumian. And intrinsic, the number of electron and holes are the same, right? So for intrinsic carrier concentration, which means that the number of electrons equals to the number of holes, are very sensitive to temperature. You can see here, it ranges, it can go from 10 to the power 6 to 10 to the power of 18 just by playing with the temperature. And this is for gallium arsenide, this is for silicon, this is germanium. Okay. Generally, the smaller the band gap, the higher the intrinsic carrier concentration. Why? The smaller the band gap, the higher the intrinsic carrier concentration. Let's take at 100 degrees. Okay. So this is germanium, this is silicon, this is gallium arsenide. So you can see, right? For germanium is the highest carrier density. Why? Sila jawab. Nak saya cerita last class. Nah.
What's the question again?
Yes, Haris?
What's the question again?
What's the question? My question is, why germanium has the highest intrinsic carrier density at 100 K, at 100 degrees Celsius? Here. In the graph.
More free carrier medium.
Yes, why of course lah, intrinsic carrier density means the free carrier. So why? For a given temperature.
Because of lower band gap.
Who's that? Apa yang cakap?
Saya because of smaller band gap.
Siapa? Saya kena cari. Who are you?
Anas.
Okay, Anas. So kalau lower band gap, then what happens?
Lower band gap means that the electrons can move more freely, can go from valence to conduction band more easily.
Why is it more easily?
Huh?
Why is it more easily?
Because the energy needed to excite the electrons is less.
Okay, that's the answer. The answer you said sebelum ni semuanya macam is not accurate and not precise. The precise answer is because germanium has the lowest band gap, therefore it requires the least energy for the electron to be excited from the valence band to conduction band. Itu jawapan dia. And that will get a full mark in the exam. If you answer yang lain-lain tu saya bagi half, kadang-kadang tak bagi makan langsung. So that in semiconductor, another thing about semiconductor, right, is very sensitive to terminology, and also sensitive. It's very precise. So you need to you need to know the question and answer directly what the question asks. Nanti I will give you one quiz, then you know kenapa biasanya first quiz tu sudah terkejut lah sebab dia tengok kenapa dia tak dapat markah. Alright, so Okay, now we go to the, so we understand, now this is just a graph to show that the intrinsic carrier density is very sensitive for with temperature. Okay, and different material, the rate is also different. The sensitivity with temperature. Okay, we also talked about doping last time. Doping means you add impurities to increase or decrease the number of free carriers. Impurities can change the conductivity of the material. Okay, and that's one of the most important features of semiconductor material, whereby you can dope it to change the conductivity. Okay, so you have all the slides, so you can go and read. My slides are, don't trust everything in my slide. So that's why you have to come to the class. Maybe sometimes it's not correct. Sama ada sengaja atau tak sengaja. So that's why if you found anything that which is not, if you don't understand, ask. Sebab tu datanglah kelas. Ada slide yang saya akan skip, ada slide yang saya akan go very detail. Right. So, okay, then the concept of donor and acceptor atom. What is donor atom and acceptor atom? Anybody? This is in your first year, electronics. Donor means a material that donates electron. Acceptor is the material that accepts electron, therefore giving out hole. Okay, so when you dope it, you can dope it with donor atoms or you can dope it with acceptor atoms. Donor atoms will give you extra electron. Acceptor atom will give you extra holes. So the rest you can read on your own. The one that I want to highlight here is the Fermi level. Have you heard the word Fermi level before? Anybody? Yes, no, don't know.
No, Adam, I think no. I
Okay.
remember.
So I will draw. You see? So okay, now energy. We learn about another one. So remember this is the energy band diagram, and you understand how we get energy band diagram from the Pauli exclusion principle, right? Go and Google, watch video on that. So if you don't understand when I mentioned in the last class, so you have the conduction band, you have the balance band. Make sure you know how to draw the conduction, because in this class you need to macam cair drawing this energy band diagram. Later we are doing a lot of drawing. But if you understand, senang je. Okay, now we have here, and then we have the gap, the band gap. Right. I told you for intrinsic. So the one that we are drawing previously is always on intrinsic semiconductor, which means that the number of free, saya tak suka dia tak straight. Kalau ada pembaris, I'll draw it straight. Okay. Okay. So intrinsic semiconductor means that the number of electrons, free electrons, is the same as number of free holes. So remember when I mentioned last time, every time you have an electron being excited over there, you always have a hole excited to the opposite direction. That's intrinsic. So normally we don't draw this. When we as an engineer, we don't draw the electron jumping here and there. So we describe this intrinsic material using a Fermi level. Okay, so Fermi level is the Fermi Fermi level is an energy level that shows the probability of finding free carriers. Okay, it's a line showing the probability of finding free carriers. It's an imaginary line. Itulah imaginary, but it shows about how do we the probability and probability to find free electrons. So the Fermi level for intrinsic semiconductor is exactly in the middle of the band gap, and it's a straight line. Alamak, saya draw ni dah agak straight. Agak balik. I don't know how to use the if you're going to draw in your exam, use ruler. Okay, so okay, so the Fermi level of a intrinsic semiconductor is exactly in the middle because the probability of finding free electron and free holes are the same, 50%. Dia macam half-half. So that's why it's always in the middle. So this is intrinsic. Okay, brothers and sisters. Now, whether it's elemental, so this semiconductor can be it can be elemental or compound. Doesn't matter. It can still be intrinsic, and the Fermi level is always in the middle because it shows. So next time, I don't have to tell you whether the material is intrinsic or extrinsic. By just looking at the energy band diagram here, kalau nampak je, if you see Fermi level in the middle, you know it's a it's a intrinsic. Tak payah cakap. Dalam exam saya tak cakap. So you should know. Number 2. Okay, so let's say how about extrinsic? Extrinsic ni we have 2 type, right? N-type semiconductor and P-type semiconductor. N-type semiconductor means you have extra what? N-type semiconductor, you have extra what?
Electrons.
Okay, so extra electrons, therefore you dope it with donor. And then P-type, you have extra holes, so acceptor. You dope it with acceptor atoms. So you have extra electron here, you have extra holes. So you have 2 types, right? So if you look in the what do you call it? For dalam, if it's physical, you want to draw it as the physical, you see like this. Okay, you have for example, this is apa nama ni? Silicon. You dope it with, for example, here you dope dengan apa ni? Something from group 5. Okay, so have normally 1, 2, 3, 4, but when you dope it, some of it we have 1, 2, 3, 4, 5. You have extra 1. Okay, so in physical, the way we show it is like this. But in terms of energy band diagram, okay, brothers and sisters, whatever you can see whatever you draw in a 2D diagram like this should be able to be translated into electronic band diagram. Okay, later on you will learn. I will teach you how do we translate. So for example, this can be translated into an energy band diagram like this. So you still have the conduction band, you still have the valence band. Let's say this is N-type material, N-type silicon, 1.1 eV. Okay, so let's say this N-type silicon is have extra electron. So let me ask you, free electron, is it in conduction band or valence band? Free electron.
Balance.
Free electron, is it conduction band or valence band?
Conduction.
Conduction band.
Yang salah tu. Nanti lepas ni kita banyak lagi nak yang lagi complicated. Ni semua benda tu kena masuk. Make sure ingat sebab tu nama dia conduction because you have electron free over there. So you have free. So you have free electrons in the conduction band. Therefore, the Fermi level is the probability of finding free carriers. So since it's n-type, this is n-type, it means that you have the probability of finding free electrons are more compared to finding free holes. So the Fermi level will be very close to the conduction band. Ni Fermi level dia. Okay. If you want to step one step back, sebenarnya ni dah shortcut sebenarnya. Sebenarnya when you dope it with donor atom, what happens is you are introducing a donor energy level inside the band gap. Kalau yang ni kan intrinsic tadi dia tak ada apa-apa. It's pure, nothing. In the band gap there shouldn't be any should not have any energy level energy state. If a pure semiconductor is the band gap, that's why nama dia forbidden band gap. There's nothing, no energy level should have inside the energy band gap. But when you dope it with impurities, it's no longer pure. So what actually you are introducing what they call it the donor energy level inside. So Fermi level is always half, always 50% between the energy level to the conduction band. So sebab tu dia duduk kat sini. But normally when we don't draw the donor energy level, terbuang. No need. Because we know the Fermi level will always be 50%. So whenever you see a Fermi level which is close to the conduction band, I don't have to tell you automatically you should know it's an n-type material. Okay, whenever the Fermi level is close to the conduction band, you know it's a n-type material. So it means that the bound electron in donor atom can be easily excited. But you can see that the energy is smaller. So that's why at room temperature, we assume all of the electron in the donor, okay, all of it, electron given by the donor atom will be excited and all of it will be here. Sebab the energy is very small. Can you digest ke tak ni? Dah faham tak? Kalau tak faham cakap.
Madam,
Yes.
if the energy level jadi tinggi, jadi kalau for the original apa ni band gap dekat apa ni apa panggil valence gap, valence band tu dia jadi apa? The valence band.
Tak faham.
Ni kan the energy gap becomes more smaller, right? So what happens to the original valence band?
Tak, bukan. Ni bukan band gap tu is the same. Okay, don't confuse. That's a good question. I didn't change the band gap. The band gap is still 1.1 eV. The band gap is still 1.1 eV. The band gap doesn't change with doping. Your thumbprint doesn't change when you eat something or you do exercising, it doesn't change. Your thumbprint is still your thumbprint. So for semiconductor device, we dope it, the band gap is still 1.1 eV. So you still have the valence band over here, you still have the conduction over here. Here is just the donor level atom. It's not the material, it's not the semiconductor material, it's the donor material. Okay, so the donor material added extra, it gives extra free carriers. So that's why I'm just telling you this so that you understand kenapa tiba-tiba you get a lot of electron there, because by adding impurities, the material with the donor, you are actually adding an extra energy level inside the band gap. which have a lot of bound electron, and this bound electron can easily be excited for you to get free carriers. So normally at room temperature, the carrier concentration for the whole material here, the carrier concentration will be the number of the donor atom. Sebab tu belajar dulu kan, I don't know if you still remember in your first year electronics, we say the material are doped with apa namanya phosphorus of 1 times 10 to the power 23 per centimeter cube. So this is the number of atoms. This is the how much you are doping. You put the apa nama ni the number of atoms. This is the number of atoms. So we say this number of atoms equals to the number of free carriers or the number of electron. Sebab ni lah we assume all of it are being excited to the conduction band. Faham ke lagi confused? Any question?
Does it mean that if we increase the higher donor density, then the ED would increase more?
The ED, okay. That's a good question. Where does this ED coming from? Okay, this ED this ED, this energy level of the donor atom, the height, whether it's there or sometimes it can be here. So the Fermi level will be here. Okay, it depends on this concentration, how much you put of the phosphorus or how much of the donor atom you put. It will vary the where it's where mana cerita. It will vary where the energy level is. So sometimes it can be here, here and here. So from here, if I kita tukar colour dia, got confused. So let's say ni conduction band, ni valence band. So looking from here, I know which ED1, ED2 or ED3 has the highest concentration, how much atom you put, the donor atom you put. So ED3 have the highest concentration because it's closer to the conduction band. So therefore, which normally we don't draw the donor level. I'm telling you, I'm just explaining to you the donor level to make you understand where the Fermi level comes from. So in the end, we don't draw the donor level. What happens is we translate this to, it will go to like this. So this is conduction band, this is valence band. It becomes, so kalau yang ni, Fermi level dia akan ada dekat sini. So between ED3 to conduction band. Yang ED2, it will be half, it will be here. ED1 to to the conduction band, it will be half. Can you understand? So Fermi level always half between the donor level to the conduction or the valence band. Valence band saya tak cerita lagi, baru cerita conduction band. So normally, if you see the Fermi level here, so now kata Fermi level dia macam ni, EF1. Then Fermi level 2 macam ni, EF2. And then Fermi level macam ni, EF3. Which one has the highest concentration of electron, free electron? The answer is 1, 2 or 3?
1.
Yes, the answer is 1 because it's the closest to the conduction band. Okay, does that answer your question, Afiq?
Yes.
Okay, good. Any more question? No? Then we'll go to P-type. So ni baru N-type. So basically N-type, Conclusion ya, N-type. N-type material. So if it's N-type, it means it's extrinsic. You have a Fermi level which is closer to the conduction band. You know it's a N-type. So P-type material, P-type materials means that you have extra apa?
Extra holes.
Extra holes. So where do you find free holes?
Balance.
Valence band, right? You get free holes in valence band. Therefore, you know the Fermi level for P-type material should be closer to the valence band. This is conduction band, this is valence band. So the Fermi level should go be here. Okay, whenever you see a Fermi level close to the valence band, I don't have to tell you, you know it's a P-type material. Okay, and the same, dia punya apa explanation the same because actually when you dope it with the acceptor atom, you actually have an acceptor energy level over there. So the hole here can be easily be excited to go to the valence band. Therefore, you get a lot of p holes at room temperature. Okay, any question? Any question? Tak ada? So make sure you remember yang ni kena ingat tau sebab lepas ni kita akan draw complex energy band device. Kita akan cantum, we're going to combine the P-type, the N-type, sometimes P-type, N-type and I. So you need, jangan confuse yang mana N-type, yang mana P-type.
Madam,
Yes.
so does that mean the P junction dengan N junction ni semua extrinsic lah? Extrinsic, extrinsic.
P junction.
P junction. P-type and N-type, is it all extrinsic?
Is it all apa?
Extrinsic, extrinsic.
Yes, of course. Extrinsic means you dope it.
Okay.
So you dope it with P-type material, it becomes P-type material, or you dope it with N-type. So extrinsic ni, yang saya cerita tadi, mana? Ni, extrinsic. You cannot have two apa nama ni, two type, extrinsic, N-type and P-type. Silicon, no, intrinsic is not doped at all, pure. Okay. Any more question? So awal ni, if you do, you need to make sure you clear, you understand, because later kita akan masuk dalam semiconductor. We don't learn a lot, but we go deep. This semiconductor device punya course. So kalau if you are lost in the beginning, will be at the end inna lillahi wa inna ilaihi raji'un. So memang tak tahu apa dah, saya cakap apa dah by the end. So if you don't understand anything, you better ask now. Sebab nanti awak akan hafal je, then no point. Dah, tak ada soalan. Semua orang faham? Oh, bagus ni. Semua orang faham. So now you understand the acceptor, the N-type, the P-type, acceptor, donor, and you're able to draw it in terms of the energy band diagram here. So you can see here, this the acceptor levels ni maksud dia EA tadi. Okay, dia tak draw Fermi level. Fermi level will be, the Fermi level will be exactly, Allah besar sangat. The Fermi level will be exactly half. Kalau nampak tak? Okay. Tapi normally after this we will not be drawing any acceptor or donor level or energy level. We'll be only drawing the Fermi level. Okay. Ada soalan? Tak ada soalan. Kalau ada soalan, just stop me anytime. So habis dah first slide. Let's go to the second slide. Okay. Oh, sebelum kita pergi second slide ni, I want to talk about the effect of temperature to semiconductor. Pergi balik sini. So as I mentioned, as you look at the graph of the intrinsic carrier concentration versus temperature, you know temperature plays a big role in semiconductor material and devices. Therefore, we need to understand how the temperature affects the semiconductor. So, tapi sebelum tu, just wondering, have you all watched the video that I put in the Telegram?
Yes.
Yes,
Apa
madam.
yang dah tengok boleh buat reaction tak? Buat thumbs up ke? So only half. The rest of you, not interested, not important, don't care. Nombor satu. Too busy. Yang tak tengok tu lah kenapa. Tengok tapi tak semua. Kenapa tak semua? Panjang sangat. Is it long? Berapa minit eh?
Dia bukan yang playlist, yang pasal TSMC sebenarnya. Maybe sister tu dia ingat yang playlist tu kot.
Macam playlist?
There's a
Maybe
genius. There's a method behind the magic.
Bukan yang playlist tu, dia ni yang
I always tell people my
TSMC.
inspiration was my destiny.
Over 30 years,
4 minit je pun. Yang TSMC tu. Siapa watch the TSMC? Can you put the thumbs up again? Pun tak ramai. Sebab saya tak ada kerja lain kan. Kerja saya bagi video yang tak penting dalam dalam Telegram group waktu. Okay. I won't give you anything which is not interesting and not important. I'm also very busy. Okay. Things that I give you is normally I find it interesting and I find it important. Have all of you been into a clean room? Ada?
Nope.
Huh?
No,
Ada
no.
Before.
siapa dah pernah masuk clean room? Put reaction. Afiq. Only Afiq alone. And the rest of you have never been a clean room. You never seen how the integrated chip factory is. Then how would you know? How would you appreciate what you are learning? That's why I'm giving you that video. Okay, I give you 4 minutes from now. All on mute now. Go and watch it. 4 minutes from now.
Yang dah tengok Adam.
Huh? Sorry?
Yang dah tengok.
Yang dah tengok, boleh tengok sekali lagi, itu pun rehat. Kau buat lah. Okay, those who haven't watched, because I will ask you, yang dah tengok tu kalau ingat tak apalah. I will watch you what you understand or what you get from the video. Okay, 4 minutes from now.
it is most likely if you have a smartphone.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand. It was this strong.
Over 30 years, Taiwan underwent massive economic and global miracles. Huge sector industry, led by a company using the big word, producing the chips inside some of the best phones.
Silicon 1,000 times.
Thanks to the discovery.
Okay, have you finished watching? Dah tu? Dah?
Yes.
Yes, madam.
Everybody watch, huh? So what,
Yes,
what,
madam.
what do you get from the video, Amirul Faris?
Okay, just not just not little information lah, just additional information. Macam she said that in the factory, the light of the factory, the yellow light is protecting the product. I still wondering why the lights, why the yellow light is used to protect the chips, because it says the light can prevent it from damaging the chips.
So since Afiq has been into a clean room before, maybe you can explain why yellow light.
I'm sorry, madam. I don't remember about that.
You pergi kilang mana itu?
5 years ago, Infineon, yeah.
5 years ago, Infineon. Okay. You know, normally, previously in my semiconductor device, I bring students to go to MIMOS. MIMOS will have a small clean room. But sekarang ni with the MCO everything, tak ada harapan lah for you to go. So that's why I'm giving you this video so that you have a appreciation of what is it. So the yellow light, brother, because there are when they do photolithography, there's a process in VLSI design. I'm sure you learn in the VLSI class. You won't be learning here. Where in the photolithography, the material that they use are very sensitive to the wavelength of yellow. It will harden the material. So that's bukan sensitif ke yellow tu tak sensitif, dia sensitif ke normal light ni. Yang kita punya normal light putih ni is sensitive. So that's why they change everything to yellow to make sure it doesn't affect the material for the photolithography. It's not the semiconductor material, the other material to make the chip or the integrated chip. Okay, so what else? I want to hear somebody else talking. Sister lah pula. Sister mana yang tak cakap lagi ni? Siti Farhana. What do you get from the video? Siti Farhana, it's the same person. Can you hear me? Dengar tak Siti? Tak dengar ke ni? Munira. Siti ni buat apa tak dengar? Dia tak bercakap. Munira? Yes. So what do you learn from the video?
I learned that the company, the factory is actually fully automated. I never sehingga ada orang banyak orang yang produce motor rupanya banyak more to automated factory.
Okay. Alright. Good. Lagi? Ikmal?
Dia nak masuk dalam factory tu kena betul-betul bersih lah.
Why?
Sebab dia orang buat chip yang
Inggris. Kita ni
because
first language English.
Because they do the chip, the size of the chip is very small. Then even one dust will affect the chip.
Yeah, even one dust will short circuit the chip. And okay, so if you it shows how what do you call it, the device are very small. You say that like let's say 5-10 years ago it was 23 nanometer, the size of the transistor. And the 23 nanometer is like thousands of your hair. Your hair ni, ambil your hair, one hair, and you divide by 1,000, that is 23 nanometer roughly. Now the technology is not 23 anymore, about 5 nanometer. Can you imagine how small it is? Cannot, mind blowing, right? This is like mind-blowing technology, and Allah has given human being the capacity to think and do this. Okay, Allah yang bagi ilmu tu. But the problem is this knowledge is this skill is very expensive. So only it needs millions and billions of investment in order to make the factory. So as you watch in the video, TSMC is a very big company in Taiwan. So remember when I do ta'aruf on myself, I work as a IC design engineer. Ada kan saya cerita ke tak ada?
Yes.
Yes, I work as an IC design engineer. It's a fabless company. There's no factory. It was just purely design. So we do design and we send to this TSMC in Taiwan to make the device for us, because they accept all customer punya request from all over the world. and they are actually very advanced. So now the big, if you look in the, if you watch, kalau you interested, there are a lot of videos out there where only certain countries have this capacity and factory to build integrated chips. Not all countries. So they'll be in China. At the previously it was because the cheap labor. Then Malaysia have, why Intel, Infineon Motorola invested in Malaysia, because of the number one, it was relatively cheap, the labor before. Sekarang dah mahal sikit. So that's why they are moving out. We are losing because they are, company nak cari cheaper, to pay cheaper salary. But at that time our labor was cheaper and it was, the political is stable. Sebab now if you want to invest the billions of money, you don't want to invest in a country where tomorrow bomb habis, right? So they will invest in a very stable country. So Malaysia was one of the stable country. But now our taraf hidup, apa taraf hidup bahasa Inggeris? Cost of
Yeah, cost of living.
Like cost of living are increasing, quality of life also increasing. So it's more expensive to pay us. Now they are thinking of nak pergi ke Vietnam, because now Vietnam this labor is cheap. So you can see the semiconductor is booming over there, and it's a problem because when they go out, their investment out of Malaysia, we have no job. The biggest economy, the second biggest economy for Malaysia is electronics and IC design. So as I mentioned before, memang ada banyak kerja. And now they are moving, and but the problem is the one that they are doing in Malaysia, the Intel, Infineon that do in Malaysia, mostly I would say 80% or more on the yang kerja-kerja buruh just to assemble, package, make the everything, just check the quality. The design and the thinking of the integrated chip are doing in US. So Intel do it in US, they send the design here in Malaysia, they make it in Malaysia. So that, which means that we don't learn, they don't give, as if you watch the video, they say sensitive information kan, ada last tu dia beritahu, because these are, people will fight, Motorola and Apple and Samsung are fighting. Who can give the latest camera with the everything, because they are all what you call it, intellectual property, and they won't give this knowledge easily to anybody. Brothers and sisters, that's why it's jihad and fardu kifayah to study the best that you can, because they won't give you easily any knowledge. We need to go and find it. Okay, cukuplah ceramah. You watch the video. I hope you learn about things and how big is the factory. When I was watching the video, I was like, wow. Dia kata 400 km. It's like satu hari, bukan besarnya factory. How far the chip will go? Like around the earth, or how many times? Macam amazing amazing how the technology is nowadays. And then it requires a lot of money. We hope that one day we have the technology and capacity to learn this. Kejap. Okay, we have a few more minutes. Let's finish this. Bismillahirrahmanirrahim. Ya Allah. Okay. Can you see? Kau nampak? Kita kat mana tu ya?
P-type.
Okay, now we want to learn on the temperature effect, right? So before we go today, I want to talk about the temperature effect. So this is conduction band. This is valence band. Okay, the temperature effects are mostly sensitive for the intrinsic carrier concentration. If it's extrinsic carrier concentration, temperature is not very sensitive. Why? Because even at room temperature, kalau kita tengok tadi kan, even at room temperature, all of the what they call it electron here will already be excited. So at room temperature, all of the donor electron tadi will already be excited to the conduction band, so no problem. At room temperature you get all the free carriers. But the problem is for the intrinsic carrier concentration. The intrinsic carrier concentration depends on the electron to gain enough energy, the energy of the band gap, to go to the conduction band. It means that the higher the temperature, more electron. Okay, the higher the temperature, more electron. And why? Because this electron over here will gain more enough energy to go. So the bigger the temperature, the more electron will be able to do that. So it will be, as I mentioned before, here in the two material, semiconductor material. So semiconductor 1 and semiconductor 2 with two different band gap. This one will be more, this one is S1 will be more sensitive to temperature compared to S2. Why? Because it's easier, less energy to overcome, to be free. Okay, so therefore, okay, in extrinsic semiconductor, okay, kita tengok tadi n-type here, is n-type semiconductor here. Let me ask you, if it's n-type, all the electrons are here, the free electrons are due to donor atom sahaja ke tak? The free electrons in the conduction band for n-type material, is it due to the donor atom alone or no? You understand my question? What's the answer?
No.
Okay, if the answer is no, then what else? Who answered no just now?
Me. Afiq.
Afiq. If no, then what else? The free electron needs to come from somewhere, right? So number one, it comes from the donor energy level being excited. Okay, good. What else? Can the electron be excited from the valence band to conduction band?
Yes.
Yes.
Yes. So meaning for extrinsic semiconductor, there are two ways of you to get free carriers. Number one is due to the donor atom. Number two is due to the excitement of the free carriers from valence to conduction band. And the same as hole, dia sama juga. However, in your first year, we always assume that this is negligible. Okay, at room temperature. At room temperature, normally this excitement of the intrinsic carrier concentration is negligible as compared to the dopant at room temperature, because normally the doping is much more compared to the intrinsic carrier concentration. Numbers are normal lah. Number normal. Biasanya kalau intrinsic carrier concentration 1 times of 10 to the power 15 per centimeter cube. This is intrinsic carrier concentration. And if if it's from donor, katalah from phosphorus ke apa ke donor, from the donor atom, normally is 1 times to the power 23 per centimeter cube. So you can you can see the difference here, right? So 10 to power 15, 10 to power 23. Jauh beza. That's why normally if you minus 10 to power 23 minus 10 to power 15, 10 to power 15 is negligible. So normally that's why we assume ni macam tak ada. But as you increase the temperature, this mechanism will get more and more important. And you cannot neglect it at a certain temperature. Okay, faham? Faham tak? Okay. Sebab biasanya sebab tu ilmu ni dia ada ilmu tadika, macam tadika belajar senang je kan. Lepas tu masuk darjah 2, darjah 3 bila ke universiti, you learn things that you don't learn in tadika. So first year dulu you assume senang. Kita make a lot of assumption. As you go deeper, belajar elective, fourth year, master, PhD, then you will learn more detail. Which means that it's only a bit, the assumption is only valid for room temperature. As you increase the temperature, the intrinsic carrier concentration becomes more important. Okay, good. So up to here, so temperature effect done. Scattering, okay, mobility. I think next class. Okay. Next class we'll be learning about mobility, scattering, and drift and diffusion current. Lepas tu kita akan masuk PN junction. After PN junction, okay, make sure you fully understand the PN junction, because after that is the assignment. You're supposed to explain about the optoelectronic device based on the PN junction. Okay, ada soalan?
Based on the effect of temperature, right? So does it mean like if we increase the temperature that we reduce the band gap by increasing the temperature, which would cause the higher chances of the semiconductor device to fail?
Increase?
Decrease the band gap by increasing the temperature.
The band gap doesn't change with temperature for this level lah. Your level sekarang ni kita belajar level 2, sekejap lagi kalau level PhD lain. So for now, because it needs a very extreme case in order to change the band gap. So for now we assume temperature doesn't and doping doesn't change the band gap.
Okay.
The band gap doesn't change. Dia macam thumbprint kita lah. Dia tak akan tukar kecuali awak pembedahan dia lain lah. Tu cerita lain.
Okay.
Okay? Does that answer?
So the one that the effect of the temperature is based on the intrinsic carrier, right? The change of the density of intrinsic carrier.
Yeah, intrinsic carrier concentration.
Sorry.
It does affect the extrinsic, but at room temperature, all of it already being excited. All the extra electron in the donor level already excited. So tak penting pun discuss because it's already excited. Tapi yang intrinsic carrier concentration, yes, it's important.
Right. Just want to clarify, I got confused between the intrinsic carrier concentration and the band gap based on the image that you draw earlier. All right.
Okay.
Now it's much clearer. Thanks.
Okay. Good. Any more question? The rest of you dah berasap lah. Tak berasap kan? Senang kan? Kalau faham senang, jangan lupa ya. Kena selalu, you know, how to make the knowledge retain in your mind. Anybody can tell me macam nak boleh senang ingat, jangan cepat lupa.
Perform discussion.
Okay, maybe. Others?
We need to understand.
You can understand. Yes, lagi?
Tulis dan baca.
Tulis dan membaca, yes, it helps. I will tell you the story of Imam Shafi'i. Have you heard the story of Imam Shafi'i and Tok Guru dia and his teacher? Siapa tahu cerita ni? Sila ceritalah. Sahabat-sahabat nak tahu. And saya tak reka cerita ni. So one day, so Imam Shafi'i is very smart and has a photographic memory. Macam excellent. So you know why? And Allah gifted him. So one day he was walking, and then okay, guess what happened? Tiba-tiba Muhaimin jalan, dia jalan-jalan, dia ternampak perempuan yang cantik. So jadi sebenarnya bukan nampak perempuan cantik. Imam Syafi'i saw dia macam jalan tu terbuka aurat perempuan tu. Kat zaman tu everybody are covering the aura. Can you imagine now? You jalan sekejap je masuk dari LRT tu habis dah semua dosa yang buat. Can you imagine, saya takut naik LRT. Saya perempuan pun takut naik LRT, sebab banyaknya dosa boleh dapat. So this Imam Syafi'i was walking and then he saw, dia ternampak kaki seorang perempuan. And then lepas tu dia hilang memory dia. And he was very shocked. Dia terkejut lah, kenapa dia tak boleh ingat ni? Normally dia boleh ingat. Then he went to see his teacher. Say, my teacher, what happens to me? I'm very afraid that now I cannot, many things I hilang from my memory. And the teacher was saying, al-ilmu nur. Teacher dia kata, this knowledge is light, cahaya. Okay? And Allah tu pun cahaya. Banyak benda cahaya, ada surah pasal cahaya dalam Quran. So al-ilmu nur. Ilmu ni cahaya and ilmu tu akan hilang bila ada dosa. So sebenarnya dia tanya Imam Syafi'i, what happened today? And Imam Syafi'i cerita dia ternampak ni, dia kata, bertaubatlah kamu. Do taubah. And then the Imam Syafi'i do taubah and again the memory come back. So brothers and sisters, kalau kita banyak sangat dosa, kita akan susah nak ingat. Ilmu itu cahaya and cahaya itu akan duduk dalam hati. Kalau kita banyak dosa, ilmu tu takkan duduk dalam hati. Sebab even semiconductor device, the ilm is from Allah. This is all ilmu Allah, bukan ilmu saya. So Allah akan letakkan pada orang yang hatinya bersih. So kalau kita selalu lupa, my advice to you, stop the sin, whatever sin you do, and then ask Allah for forgiveness. Buat solat taubat. And try to jaga mata, jaga hati, jaga akal. Kau main game tu kan, selalu pop up benda-benda perempuan tak pakai, tu pun berkacau tau. Saja nak beritahu. So especially brothers and sisters pun you kena jaga, sebab tengok aurat perempuan lain pun dosa. Laki lagi lah, saya tak tahu macam mana nak hidup akhir zaman ni. So you need to take care of your eyes, because Allah will ask you. And satu lagi dia akan affect your knowledge lah. Okay brothers, I think that's enough for today. Moga Allah bagi kita ilmu yang baik. Kita ada doa Nabi ajar, berilah kita ilmu yang baik, dan ilmu yang baik akan melekat pada kita. Orang yang baik, ilmu dia akan ingat, dia akan ingat sirah, dia ingat hadis. Allah akan bagi dia ilmu tu melekat pada diri kita. Kalau kita selalu lupa, kita kena question diri kita. Adakah kita ni banyak dosa ke tak? Kalau ya, jom kita minta ampun dengan Allah. Okay, so until next class, can we have somebody to recite a doa, brother? Gila-gila kan? Siapakah gerangannya this time? So better prepare lah next time. Tak payahlah tak payah bahasa ni bawa nak Google ke apa kan.
Amin, madam.
Okay Anas. Tak pernah baca lagi?
Belum.
Okay, silakan.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma inna nas'aluka ridhaka wal jannah wa na'udzubika min sakhatika minan nar. Allahumma innaka 'afuwwun karim tuhibbul 'afwa fa'fu 'anna wa walidina wa li jami'il muslimina wal muslimat wal mu'minina wal mu'minat al ahya'i minhum wal amwat bi rahmatika ya arhamar rahimin. Allahumma inna nas'aluka 'ilman nafi'an wa rizqan thayyiban wa 'amalan mutaqabbala. Allahumma inna na'udzubika minal baras wal junun wal jazama min sayyi'il asqam. ربنا ظلمنا أنفسنا وإن لم تغفر لنا وترحمنا لنكونن من الخاسرين. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. صلى الله على سيدنا محمد وعلى آله وصحبه وسلم. سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Alhamdulillah Rabbil Alamin. Let's close with tasbih kafarah. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Okay, Assalamualaikum warahmatullahi wabarakatuh.